The organization of the periodic table allows us to predict some things about atoms. And so we're going to look at two of those things. So what we talk about is something called a periodic trend. And a trend is just a pattern. And so there's two things that we can predict. One is the atomic size. Now, another way sometimes, and it confuses people sometimes, I've seen it also called the atomic radius. Because if you think of the atom like a circle, the radius is from the middle to the outside. So that would the radius would also be a way to think about the size of the atom. So in general, as we go from the left-hand side of the periodic table over to the right-hand side, you can see that the size decreases. It gets smaller. So if I was looking at the two elements on either end, so let's say this is lithium over here, and going all the way across, this is neon over here, then I would say neon is smaller than lithium, because as I go from left to right, the size decreases. Now I like, since I did left to right decreases, then when I go in a column or a group, I'm also going to do decreases because that's just my personality. And so if to make it decrease, we see that the size in general decreases as I go from the bottom to the top. So if I'm over here, there's neon over here, and radon is way down here. So I would say neon is smaller than radon, right? Because it decreases as you get go from the bottom to the top. So in general, we have the smallest atoms up here. And so in the opposite corner down here in the bottom, these are going to be the largest atoms. So another way we know that the metals are on the the metals are on the left-hand side and the non-metals are on the right-hand side. So in general, metallic atoms are larger than non-metallic atoms. Now we can kind of explain this to the size decreasing across the group from left to right is a little harder, I think, to understand. But the reason it does is because when you're in a period, a row, all of those elements in a row have electrons in the same energy level. And as you go from left to right, each time you move to a new element, you add an extra proton. And that proton means your nucleus is getting more positive. So as you go from left to right, the more positive nuclei pull that whole level, and they get smaller and smaller and smaller. It's kind of how you can think about it. Now it's a little easier to understand why the atoms on the bottom might be larger than the ones on the top. Because remember, as we go down from the top to the bottom, if we're thinking of electron configurations, each period we go down, we're adding a new energy level. So by the time you get to the bottom of the periodic table, you have 6 or 7 energy levels, which makes those atoms on the bottom a lot bigger. So one thing we can predict is atomic size. And we can't really predict a number. And the transition elements don't follow the trend as well as the main group elements. So this is a general kind of thing. Just knowing what would we think in general. So we won't predict numbers. And sometimes, like in the transition elements, the trend is not as clear. And so I won't ask you about transition elements because if you look, their trend is not as clear. Another thing we can look at trends about are the ionization energies. And to make an ion, we'll learn in the next chapter, you either gain or lose electrons. The ionization energy is the energy to remove an electron. And when they measure it, it's in a gaseous state. Okay, so it's energy to remove an electron. And so here's the trend. As we go from left to right, the ionization energy increases. It gets higher, which means that it gets harder to remove an electron. And if we look in a column, the ionization energy increases as we go from the bottom to the top. So we have the smallest atoms, and we have the highest ionization energy. And down here, we have in the bottom, we have the largest atoms and the lowest ionization energy. So if I'm looking at these two examples here and wanting to refer it to ionization energy, so neon is smaller than lithium. Here's neon. Neon has a higher ionization energy. It means it's harder to remove the electrons from a neon. And then if we were doing on a column here, down here it says neon is smaller than radon. Neon has a higher ionization energy than radon. Okay, whoops, I forgot. This is when I'm comparing, to lithium, and this is when I'm comparing to radon. I kind of worked my way over there. So let's look at an example. Let me find an example to make sure that you kind of see the kind of question that might be asked. So if I had 3 elements, let's say I had phosphorus, silicon, and sulfur. Now on my little periodic table here, and I am going to take the eraser and erase this so we can look at it a little bit clearer together. All right, so on my periodic table, if I were drawing them in, they're here kind of on the second row, and I have a silicon is right here if you were looking, then phosphorus, and then sulfur. So if the question was, arrange the elements in order of decreasing size. So in this group right here, who's the smallest? Okay, well, it would be sulfur, right? So sulfur is smaller than phosphorus, is smaller than silicon. Why? Because the size gets smaller. So this is the order of the size. Sulfur is the smallest. Now what about the ionization energy? Well, the ionization energy gets higher as we go this way. So the smaller atom has the highest ionization energy. Whoops, except if I would write it right. I'm sorry. So silicon has the smallest, and then phosphorus is greater, then sulfur is the highest. Okay, so it's an inverse relationship. The smallest atoms have the highest ionization energy. I like to think of it this way. So here's a nucleus, and if you're small like that, your electrons are really close to the nucleus, so they have a high attraction. If you had a big nucleus and your electrons are way out here, that's a long distance. So the big atoms, they don't feel as much attraction. So those are just 2 of the trends that we can generalize using the periodic table.